Vale, we are live now, so we can start whenever you want, okay?
Perfect. Thanks very much. So welcome everyone to another seminar in the SMAC series. We are at number 7, and today we'll...
We're live now, so we can start when...
Okay, I'll restart. So welcome to SMAC 7, another seminar in the series, and today we will be talking about the network and the computing resources at the IAC. So this is mainly intended for those here, right, at the Institute. We have 3 speakers today, Esteban, Juan Trelles, Isaac Alonso. Well, I will start by giving some overview of the resources we have, and then they will be talked about different aspects. Let me share my screen. As usual, please keep your microphones closed and cameras, and we'll have later questions that you can post. That you can post the questions through the chat, or request specifically if you want to actually pose yourself the question through the chat as well. Okay, let me get started here. Well, the IAC has a fairly large network that connects all of the computers inside, and also with observatories. This network has some few hundred workstations. Most of them have been in the past in Fedora, and now we are transitioning to having Ubuntu, homogeneous version of Ubuntu in all of them. The network is shared, and the computers are shared. So if you have an account at the IAC, that means you can not only use your own computer, your laptop or your desktop, the one assigned to you, but you can also log on to others and use them. The policies are simple: not to disturb your colleagues, be courteous. But if you need more computer power than what you have in the machine assigned to you, then you can connect to others and use them. There is also disk space that you can use locally in those other workstations in the net. Well, you have to just be prudent and not to abuse these resources. The main tools you're going to need to move on around the network and change from one machine to another will be SSH, and also DF, that will allow you to check the space available in the local disks. Usually we call the space for computing, the storage space, scratch, right? So these are hard drives or partitions in the hard drives that give you a space to work and have limited space, but usually enough. You can create your own directories there, and they are not backed up. So unlike your home directory, what you put here is temporary. If you need a backup or want a backup, then you have to do it yourself. The computing services will not do that for you. And of course, it's shared with others. So unless it's your own workstation, you have to always try to keep it clean and use it as you need. Then when your computations are done, or shortly after that, try to remove it. I will just give now some examples here, how you would do that. For example, here, I'm on my laptop. I can connect to another machine with SSH in the network. I have my SSH keys ready, so it shouldn't even need to ask me for my password here. I can jump to another machine from here using, again, SSH. And you can check how much space available there is with DF. There is some -H that changes the format to something easily readable. So you can see here these three columns. The first one gives you the size of the file system, the size that is being used, and the one available, right? So you can, for example, here in Denso immediately spot hard drive, for example, this one that has 18 terabytes. Usually, as we call them, scratch, you can grab scratch here and you will get exactly this is the one that is normally used for scratch work. Okay, there is, in addition to this scratch space in the computers, there is of course your home directory, and this lives in a file system that we call the NAS, that is backed up daily and also has redundancy, right? So it's quite a safe place to work. But of course, the speed at which your programs can access that space is much slower. So that's not for computing. For computing, you should use the scratch space. And then, of course, we have some special computers to do parallel computing on other things like, GPU to do machine learnings and things like that. And that will be described in following slides. And I will now pass the word to Anna, so she continues talking about these burros.
Okay, hello everyone. I'm going to share my screen. Okay. So I'm introducing the burros, as Carlos said. So what are those burros and what are their names? This is the first thing we have to think about. Burros is the name for high performance Linux computers. They are made for users who need to run CPU or memory intensive jobs, which are unsuitable for their own PCs, for example, or they are not enough for other IAC supercomputing resources. So I listed here some of the advantages. They are open to any user that wants you to take advantage of them. They have an easy access. So as Carlos said, a SSH connection, and they don't require any advanced reservation. So in principle, they are easy to use. These are the name of the IAC burros. I split in two groups, Deimos Diva and the other three, because Deimos and Diva they have quite different characteristics. We will see in one of the next presentations from Isaac. He's going to explain a little bit more about them. So yes, we have here the names. And so what are they useful for? And what are my responsibilities as a user? No? So in principle, they can store scripts or inputs that we need to run our computational jobs. I put here the example of HTCONDOR. Juan Carlos is going to talk us about Condor, but it is another resource that we can use. And for that, maybe we need to test before our scripts or whatever we need. So the burros are very, very interesting for that. And also developing, debugging, and testing parallel applications before submitting them to other supercomputers. However, the user has to know that there are some rules to follow. The first one is that we have to check that the load does not exceed the number of cores before launching and after our program starts. No? Here I highlighted two tasks, uptime or HTOP. Now we will see how they work. Let's see if we can. Okay, do you see my screen? I think yes. I am now inside Denso. So with the command HTOP. No,
No, we don't see it.
Okay, let's see what happened here. I will stop sharing and now sharing again. Okay. Now? Okay. So I was just in, let's see, in Denso. Okay. Well, I just wrote HTOP in the Denso machine, and this is what we get. So in the top in the top part of the screen, we see numbers from 1 to 64. These are the threads of the Denso computer. In MEM, we see the RAM memory that Denso has. And one of the most important things, well, we see that from in the threads, no, the percentage of usage, no, that they currently have. And then in the load average, we see 3 numbers there, 17.10, 9.17, whatever. These 3 numbers are the CPUs running in 5 minutes, 10 minutes, and 15 minutes after our program starts. And it is very important to know that we have to be careful with these numbers so they don't exceed the number of threads that we have, no? So, and here in the lower panel, we see we can see the the things that are running or the things that are happening in Denso. For example, Carlos is here, and me too, and whatever. No, so this is the example of how can we check, no, the load and check the number of cores that we are using. Now I'm going to share again the screen. Sorry for the talk. Okay, this was the number 1. No, the number 2 rule to follow is for parallel codes. Sorry, check how many cores are being used and don't check up all of them. This is also necessary for LaPalma supercomputers, for example, as Isaac would say. And the last thing to know is that some of these machines have a huge disk space. The highest is 700 terabytes, but don't abuse it and don't store data for a long period of time, because they are not there to store all your data for 1 or 2 years and you forget about them. It's only to run, as I said, scripts or inputs that you need before launching anything else, for example, Condor or other supercomputers. So here I highlighted that there will be a cleanup of the scratches twice a month to delete those files longer than 1 year. So if you need any extra storage, ask Nicola Caon about the machines that can be used for that. Because in my case, with my data, for example, I needed many space, because my laptop and my supervisor's computer weren't enough, no, for me. So Nicola could ask some colleagues, and they allow me to put my data there, no, to store my data there. But these burros are not for that, no. And that's all, folks. Now I leave. The next talk is, sorry, let me stop sharing the screen. The next talk is my mate Juan Carlos. He's going to talk about Condor. So whenever you want.
Thank you, Ana. I'm going to share my screen. Well, good morning, everyone. I'm going to talk about HTCONDOR at the IAC. I will start doing a brief introduction to Condor. After that, I will talk about my own experience using Condor. I will also talk about examples of submitting files and some useful commands. And I will finish reminding that we have to put Condor in the acknowledgements of papers in order to keep it alive. Well, what's HTCONDOR? HTCONDOR means High Throughput Computing System, and it was created at the University of Wisconsin in 1988. The idea behind Condor is simple. We can use idle machines to perform computations while their owners are away. So Condor is an application that is installed in pieces of the IAC to make it possible to run a large number of your computations at a time in different machines when they are not being used. This way, we don't waste computation time. How can Condor help us? Well, Condor is very useful when you have an application that has to run a large number of times over different input data. Let's see an example. Imagine you have a program that carry out some calculations taking an image file as an input. If the processing time is about 1 hour per image and you want to process 250 images, using only your own machines, you would have to wait more than 10 days to get all results. However, using Condor, you might get all results in just 1 hour, because Condor distributes the images to the idle machines at the IAC. How powerful is Condor? Well, Condor calls a slot the unit that executes a job, typically a CPU or a core if the CPU has several of them. With number of 2017, the IAC had around 900 slots that might execute applications submitted via Condor. It means that more than 21,000 hours could be available to run Condor jobs. More than 2 years of computation time in just 24 hours. But this is just the maximum theoretical limit, of course. The number of available slots depends on people using their own machines and people using Condor. Which machines are running Condor? Well, Condor is already installed in most of the desktop PCs running Linux that we have at the IAC headquarters in La Laguna. The total number of machines is 230, with the numbers of 2017, remember. Who can use Condor? The answer is anyone. Anyone with a computer account in the IAC. If you can log in on a Linux PC desktop connected to the internal network, then you should be able to use Condor without problems. How does it work? Condor is a batch processing system, so you only need to submit your jobs to the Condor queue and it will do all the work. The submission is done using a Condor script where you specify your executable, its argument, inputs, outputs, etc. I will show you an example of submission script later. Now I'm going to talk now about my own experience using Condor. I got this data using the Gregor telescope. It is a quiet sun map where you can see the granulation. In the x-axis we have the slit, and the y-axis we have the position of the slit. In each pixel of this map, I have the Stokes parameters that you can see here on the right hand. Using an inversion code called SIR, we are able to obtain solar and no-field parameters such as temperature, lone side velocity, and the magnetic field vector for each pixel. Moreover, we use SIR with different initialization, and hence the computation time increases. Well, Condor helps me because I can split the whole map in small maps. Then Condor distributes the small maps into the idle slots at the IAC. This way, we can decrease the computation time in a factor normally between 50 and 400, depending on the available slots of that time. This is an example of a submit file for Condor. In these two lines, these two lines are the base name of the submission. The cluster is different for each submission, and the process is different for each job. In my case, the submission would be the whole map, and each small part of the map would be a job. In these lines of here, you force Condor to write in the specific file the output and the error generated by each job. Here you can select the universe, and with these two commands, you tell Condor that input files have to be copied to the remote machine, and output files must be copied back to your machines only when your program is finished. And this is a loop I have for my calculations. These are the commands I use more frequently when I use Condor, but there are many, many more. You can check all of them in the CA webpage about Condor. The first one, Condor status submitters, tells you about people using Condor. In this screenshot, I'm here using 200 slots. Condor submit is just for submitting the files. With Condor queue, you can check the state of your submission. In this screenshot, I'm running 195 jobs. In my cluster, 854, and I have still 900 slots in the queue. Condor RN is just for doing jobs. Condor release is used when some of your jobs have failed, sometimes happen. If you fix the problem, you can release these jobs using this command. Condor tail display on the screen the last lines of the output of a running job on a remote machine. So with this command, you can check whether your job is working fine or not. And the last one is for checking your priority. And this is important if there are many users using Condor. As an example, I'm going to share with you my my terminal. Good. I'm going to show you one submit file. This one, for example, with everything I explained before. This is the place where I have the input files. And you can submit using the command condor submit. And it's already done. It's very easy. And you can check the status doing this. This is the submission I have just done. And this I did yesterday because it's a real one. I'm using Condor right now. Let's go back to the presentation. Finally, it's important that if you use Condor, please put this text in the acknowledgements of your publications. You can check web pages about Condor and the CEpedia for more information, or contact with Nicola Cao, who is the current local administrator of Condor at the IAC. And that's all for my part. Then incoming speaker is Isaac Alonso, and he's going to talk about Deimos, Diva, and LaPalma. Go ahead, Isaac.
Okay, hello. I'm going to start sharing. Okay, so I'm going to speak about Deimos, Diva, and LaPalma. I hope that you can see my presentation. So Deimos and Diva are a pair of burros, but they have a special configuration. In this case, I show here more or less how it is the architecture of both systems. So we have one node that is Deimos and the other one that is Diva. We can connect to Deimos using a standard SSH, as Carlos has shown before, from the intranet. And Deimos has the most important thing is that it has two different GPUs, graphical processing units, that traditionally has been used, for example, for computer games and all that. But now they are starting to be used for computations, even more now with all the advances in machine learning. So machine learning applications can take a lot of advantages of using GPUs. But also normal codes, let's say, more standard codes can be adapted to run on GPUs, and they can run a lot more faster. But this requires some special coding, so either using CUDA or other stuff that are out of the scope of this talk. Also, Deimos has 20 CPUs in total, and 11 terabytes of scratch, and 1 terabyte of RAM. It doesn't have a lot of CPUs because the main idea of using Deimos is to use the GPUs. You cannot use Deimos to run the standard CPU work here, because otherwise you get the system stuck. And the other main purpose of Deimos is to serve as the login node for Diva. And this is very different because you cannot connect to Diva via SSH. Instead, it is somewhat similar to the Condor system. You need to use Slurm, which is a queuing mechanism. So from Deimos, you submit jobs that can be run on Diva. And Diva is a very powerful machine. It is just one single node with almost 200 cores and a lot of RAM memory. So it is ideal for either parallel applications that you share memory, for example, multi-threading or OpenMP, but also for single thread or just a few threads, but that requires a lot of memory. So the idea about this is that you ask for time in Diva, like for example, a few hours, for example, 20 CPUs, and then it gets in the queue, and depending if the time is available or not, they put you in the queue. Okay. As always, there is a lot of information both in the wikis and the man page, for example, for using Slurm, or even in the internal wiki. So I recommend you that if you want to use this system, read that. So now the other system that this is even more special, let's say, it is LaPalma. LaPalma is a supercomputer that is part of the RES, the Red Española de Supercomputación. And in general, to access this kind of systems, you need to ask for time to the RES. But in our case, we have some granted time for IAC people. It is similar in the, with Deimos and Diva in the sense that you connect with SSH to a login node where you cannot use the CPUs for running your programs, but you just use the login node for maybe compiling and other stuff, and then you queue your work to the big system. So basically, we have each of these small boxes, is a node with 32 gigas of RAM and 16 CPUs. And then we have 256 of them. If you run, for example, a job with 16 CPUs, it will get allocated in one node. But for example, if you request more CPUs, you will be allocated more CPUs, more nodes, and they are not sharing the memory. So you need to take that into account in your jobs, for example, using MPI or similar. This kind of configuration is the typical for most supercomputers in the world. So it is a very nice practice to run jobs here. Also, from more like a, I think that for PhD students, it looks very nice that they have run things here, because then when you apply for computing times in other supercomputers, you can say, okay, I know how this works. I have compiled things here. I have run it. So it is very interesting to have this kind of experience. And we are lucky here that we have a lot of time to access this computer. Okay, so again, there is the wiki for this. It is very extensive, so yeah, I encourage you to read it if you want to apply for time here. And so now I'm going to show an example of this of Slurm. So just in my terminal, I guess. So basically, I'm connected to Deimos, and I can check whether, for example, as and explain with each topic someone is using Deimos. Well, no, there is someone using almost all the node. But most importantly, as I said before, Deimos is not only CPUs, but also GPUs. So I can also check the status of the GPUs with this command. And this will tell me, okay, you have 2 different GPUs and how much memory is being used in each one of these. And also the different programs that are asking for resources of the GPU. So in this case, we have one process here, but that same process is not using any GPUs, which is not recommended, but it may happen in some cases, because this system is also shared with engineering people that they use the GPUs sometime. So yeah, if you want to use the GPUs here, make sure that the GPUs are not already being used. So going to Diva. So I have here a few examples. Basically, the submission script is very similar to what is done with HTCONDOR, for example. So the main stuff is happening here. Here you are asking Slurm for a job with this name, with using one node. That with Diva we only have one node, so it has always need to be one. But for example, in LaPalma you can use more. Then I want to run 10 different programs, and each one of them 50 cores. In this case, this won't work because we don't have enough cores, but we can do this. And then this is just for 30 seconds, but you can put here up to 72 hours, which is 3 days. And then save the outputs in these files. This would be like the standard output, and this would be the error. And I have here just a simple print printing stuff. And for running parallel jobs, for example, that use MPI or OpenMP, you need to use the command srun. So in this case, it will print the first part just once, and then this command will be get executed 10 times, sorry. And then this is as simple as sleep. So the way to submit this, that's S batch. It says that it is submitted, and I can check with SQ that is here. And it is asking for 50 CPUs, 5 times 10. And I can check the output. It has generated 2 different files. And I can look for them. And it says, okay, you asked for 10 processes, each one with 5 CPUs. And for each one of them, it has printed where we are, that is in Diva. So this assumes usually that you have some application that can be run with MPI or OpenMP or similar things, but Slurm can also be used for running things similar to HTCONDOR. Here, it is in general called like job arrays. So in a similar way as before, you can have the simple batch script, and then you say, okay, I want an array of jobs. And there are different ways to indicate that. For example, I want an array of 10 jobs, numbered from 0 to 10, or from 1, 2, 3, 4, 5, and then 9, because I don't know why you want that, but you can do that, or from 0 to 20 in steps of 5. And then you will have this number. And this number will tell you for each, this will get executed the times that you need in the array, and this number will vary depending on which array you are. So let's try, for example, the easiest one, that is 0 to 10. And then I will just ask for 1 CPU, 1 task. So it will generate 10 different outputs. And if I do this, for example, I will get all these different jobs. They're running on the same time. And I will get a lot of outputs. If I check, for example, the output number 4, I will get that this was the task number 4. So depending on this number, you can make your own scripts to, for example, input this number to a Python script, and depending on that number, go to one part of the image or the other, or what you want. So it is a very, very, very powerful thing. It may happen, nice things, right? But it may happen that you realize that something is wrong while the code is running. So in this case, you can use as cancel and the ID of the job. And this will cancel all the different jobs that were being run before. And I think that more or less, that's everything that I wanted to say from my part. Let me check. Yeah, one thing more. You can check the status of Diva with SQ, and it gives you the number of CPUs that people is trying to use. But there is another more simple command that is sinfo, and you ask for the number of cores. And here it lists you the number of active CPUs. Inactive CPUs, this is the total amount that you can ask for now, and the total available in the node. So for example, if I run a very big job that is requesting more CPUs than there are, it will get in the queue because there were not enough CPUs available now. So it will stay here because there are not enough resources. And when these jobs finish, luckily, my job will be run. And until then, I can sort of forget about that. And that is all. Compared to Condor, the main difference here is that you are sure that if you ask for 20 CPUs, you will have the 20 CPUs just for you. So it is very convenient when you run applications that need to, for example, you are measuring the time that some application is taking. So that is very useful then, because you are sure that no one is messing up with the CPUs that you're using. From my side, I think this is all, and I will leave you with Carlos to finish.
Thanks very much, Isaac, and Ana, Juan Carlos. I'm going to go back to share my screen here. Okay, well, we don't have much else to say. A few things is, well, that of course, all of the computing services we have are here at your service for all of the researchers, engineers at the center to use and exploit and make progress on their work, satisfy their needs. Access to, as I mentioned at the beginning, access to the workstations is direct using SSH. Then access to the supercomputers, to the big ones, LaPalma and Diva, to put jobs in those queues. We have some basic rules. You have to request to be added to the users able to submit jobs. This is to have some minimal control by writing to res_support@iac.es. Access is available to anyone that wants to do scientific computations, and no questions are asked. Basically, you just have to say, well, I work on this thing, but you don't have to really give details. But what we ask you, and these are rules that have been evolving, and now we are implementing, starting with the new year, we will request you a yearly report. So at the end of the year, you have to send to us, to the computing services, a brief report stating what you've done. If you have published papers, and made sure that you included the acknowledgement in them. Tell us which papers, and automatically that will renew your access to these machines. This is also mainly intended also for improving the way we track productivity and activity, which is important for upgrading these systems and maintaining them in the future. We have the CUSI, the Comité de Usuarios de los Servicios Informáticos, that has a large number of researchers in them, and that will be the reviewing committee that will look at these reports. And to finalize here, we'll also underline that these explanations were meant basically to give you a brief introduction of the systems we have at your service. But of course, this is far from sufficient to really get you started. But there is plenty of documentation in the internet, the CA pages, the CApedia, includes a lot of information and examples on scripts to use these machines. And you can ask us. We are here to help you getting started. Of course, we have the CA, Nicola, Jorge, and we have as well new people getting in the CA, especially devoted to supercomputing, starting in January, and also other people working on machine learning and AI and other things that will be able to help you if you need. And there is, of course, the whole computing services, the whole information technology group that you can ask, and you can, for example, write to COW for any needs you may have. And of course, there is a lot of more experienced users around that you can ask them, other students, postdocs, researchers around, and you can ask me, of course. So with this, I will just end, and maybe we can have some questions. If people, okay, let me stop sharing here. Let's see if anyone has any questions or comments. Let's indicate so in the chat.
There is one question in YouTube.
Okay, I cannot read that. Maybe you can formulate the question.
Yes. What network speed does the IAC use? He says that it often falls down when transferring large data sets around the network.
Yeah, okay, I mean, I don't know the exact number. I think it's gigabytes, right? It's a gigabit network, but I don't know the exact number. I know that I can tell you that, well, inside the network, normally things look immediate. So it's really, the latency is really negligible within the main headquarters, and the same happens when connecting to the observatories. There is dedicated fiber connections between the different centers of the IAC, the CALP, where the supercomputer LaPalma is, headquarters here in La Laguna, and also the two observatories. So the latency is really minimal. Any other questions to me or any of the speakers?
Well, it seems everyone understood everything.
Yes. Okay, maybe we can also take the opportunity to comment that, usage, for example, of Condor at times was in really high demand, and it wasn't that useful for a few people to really get because it's a shared resource, right? So it was hard to really get the use of it. And but in the last months, year or so, I think the demand is not so high. So it will really pay off to those getting started with it to get a lot of CPU hours. And in LaPalma, we should also say that the machine is part of the res. We are part of the res, so users can apply to res for time there and in other computers of the supercomputing network in Spain, but the IAC has reserved half of the time, and that's really of order 10 million hours or so per semester. So it's a lot of time. I think we can finish here if there are no more questions. Thanks very much, everyone. And
thank you for coming, everyone.
See you next time.
Thank you.
Thank you, guys.
Thank you.